this video is on properties of solutions. So as you know, we can measure the concentration of solutions in a variety of ways. We can measure it using molarity, which is moles of solute per liter of solution, which we show by a capital M. Molality, which we show by a lowercase kind of italicized m, which is moles of solute per kilogram of solvent. Mole fraction, which we use this fancy X or the chi, which is moles of A divided by your total moles, so A plus B, usually the moles of solute plus the solvent. And then we have mass percent, which is where we look at the mass of our solute divided by the total mass of the solution times 100. So let's put this into practice. If I have a bottle of 100 grams of a 37% solution of hydrochloric acid, I can therefore calculate the molarity, the molality, and mole fraction of hydrochloric acid if I know that the density of solution is 1.19 grams per milliliter. So the first thing I want to calculate is moles of my solute. And my solute in this case is hydrochloric acid. So to do that, convert grams to moles, and I get 1.01 moles of hydrochloric acid. Then molarity is moles per liters of solution. I'm told I have 100 grams of my solution, and I know my density is 1.19 grams per milliliter. So I can convert from grams to milliliters, and I need it in liters, so milliliters to liters, and I get 0.084 liters. So I take my moles, divide by my liters to get my molarity of 12 molar HCl. If I want to calculate molality, I already have my moles of solute from here, so now what I need to find is my kilograms of solvent. Well, my solvent is water when I make an aqueous solution. I have 100 grams of my solution. Subtract from that the mass of my solute, which is my hydrochloric acid, and then that leaves me with 63 grams of water. So that means to make my solution, I measured out 37 grams of concentrated hydrochloric acid, and then I diluted that with 63 grams of water to make my 37% solution. Now remember that when we see percents, we can figure they're out of 100 to make our lives easier because it's a part out of the whole. We can decide what each of those are. And so that's why we have a 100 gram solution in this case. So I take my mass of my solution minus my mass of my solute to get my mass of my solvent, and then I convert my 63 grams to kilograms, which is 0.063 kilograms. Take my moles divided by my kilograms of solvent, and I get a 16 molal solution of hydrochloric acid. Finally, to calculate my mole fraction, again I know my moles of HCl from up top. Then I need to figure out my moles of water. I know that there's 63 grams of water in my solution, so converting grams to moles, I get 3.5 moles of water. I want the mole fraction of hydrochloric acid, so I take the moles of hydrochloric acid divided by my total moles of solution, and I get 0.22 as my mole fraction. Remember that when we make a solution, we can only dissolve things in one another that have the same polarities. So a polar solution and another polar solution, or a polar molecule and another polar molecule would be soluble. Nonpolar and nonpolar is soluble. But if I were to try to mix a polar and a nonpolar molecule together, they'd be insoluble. So our classic polar molecule is water. Our classic nonpolar molecule we think of is oil. And that's how we can remember too that oil and water don't mix because one is polar and one is nonpolar. Solutions are made because of entropy. And entropy is nature's trend towards disorder. It drives the solution's formation. So if I were to make a solution of this solute with the solvent, what first happens is I put my solute in my solvent and it's going to first expand. So my solute starts to expand, my solvent starts to expand. Once they're expanded, they then mix together, and this is much more disorder. It's kind of like chaos, right? Everything's all mixed up in my solution. Whereas here, they are all neatly organized, my solute and my solvent. So we think of this disorder, entropy, so as they're coming together, they kind of mix together, so they spread apart, then they mix to make our solution. So there's 3 steps to form a liquid solution. First, we separate the solute into its individual components, which is called expanding the solute. So this is where your solute expands into its individual molecules or atoms, depending upon what you have. Then, to overcome the intermolecular forces in the solvent, to make room for the solution, which is expanding the solvent. So the solvent has its intermolecular forces present, and those have to be overcome so that way it can expand to then allow for places for the solute to come between. So then, allowing the solute and the solvent to interact will form the solution. Okay, and we'll watch a few videos of what this looks like, or you can look up some videos of the solution formation of this, and you can see it, there's animations where they show where either the solvent comes in and attacks the solute to pick it apart, or that this expands and this expands, and then they mix together. Just kind of depends on the solution you're looking at. Something to note, a new term to look at, is the enthalpy of hydration. So when we are dispersing the solute in the water, there's some energy required that's overcoming those intermolecular forces and mixing together. And so this energy released by the dispersing of the solute in the water is called the enthalpy of hydration. So solubility can be affected by a couple of different factors. The first one is structure, which makes sense. Structure, the molecular structure, is going to determine the polarity, and we already know that polarity determines solubility. Temperature for aqueous solutions, we previously said that, as we increase temperature, we increase solubility. This is mostly true, but there are exceptions to this rule, and there's no real way to know if a molecule is going to be in an exception or not. So the best way to know is by experiment. And these experiments have, for a lot of cases, been done for different salts, and so you can look up a solubility curve for them, and then reading the solubility curve, you can see what the trend is. Now, pressure is going to affect just gases. So an increased pressure affects the solubility of gases. It's more soluble the more pressure we put in, but it doesn't impact liquids and solids. And this is because gases like to be spread out, and so they're compressible, and so I can force my gases into a smaller volume, whereas liquids and solids we can't do that with. This leads us to Henry's law, which is the relationship between gas pressure and the concentration of a dissolved gas. So Henry's law is that the concentration of dissolved gas is equal to this constant based on the solution. So this would be given to you, or you'd have to calculate it knowing concentration and pressure, and then the partial pressure of the gas above the solution. So using an example with this, we can think of soda. So if a bottle of Coca-Cola is opened, so that 25%, is opened, a bottle of Coca-Cola is bottled so that at 25 degrees Celsius, it contains carbon dioxide gas at a pressure of 5 atmospheres over the liquid. Assuming the partial pressure of carbon dioxide in the atmosphere is 4 times 10 to the negative 4th atm, calculate the equilibrium concentration of carbon dioxide in the soda before the bottle is opened, and we're going to add in and after. So we're given the Henry's law constant for carbon dioxide in aqueous solution is 3.1 times 10 to the negative 2 moles per atm liters at 25 degrees Celsius. So I'm trying to find my concentration, which is here. Now in my closed bottle, I'm told that the pressure of my gas is 5 atmospheres over the liquid. And I know that my constant is the 3.1 times 10 to the negative 2. So concentration is equal to Henry's constant times my pressure, my partial pressure. So my 3.1 times 10 to the negative 2 times 5 atmospheres gives me a concentration of my carbon dioxide in my soda as 0.16 mole per liter carbon dioxide. Now in my open bottle, I was told that the pressure of CO2 above my liquid is now 4 times 10. Well, they told me that the pressure of CO2 in the atmosphere was 4 times 10 to the negative 4 atmospheres. Well, I know that my CO2 is going to escape the soda until it reaches a pressure equilibrium with the atmosphere. So at 4 times 10 to the negative 4th atmospheres, and the pressure of CO2 inside my soda gets to that pressure, then it's going to stop escaping the soda because now it's in equilibrium. So the pressure of CO2 gas in the soda will reach equilibrium with the atmosphere, so that must be the pressure of CO2 above my soda. Looking again for my concentration of carbon dioxide, I use my same constant times my new pressure above the soda, and I get 1 times 2 to the negative 5th moles per liter. So writing that out just so you can see the difference is 0.00012 moles per liter, or molar carbon dioxide. We can see the huge difference between a unopened can of soda or bottle of soda and then a open bottle of soda. And the carbonation here is so much less than here. And that's why after your soda's been open for a while, we say that it goes flat. The carbonation, disappears. It goes in the atmosphere. And that's because my pressure, CO2, had to equilibrate with atmospheric pressure of CO2. And then it's no longer has the bubbles in my soda.